Hello everyone. So in this video I'm going to discuss the contraction mapping theorem. So I have brought one problem from the ISI book like test of mathematics at the level 10+2. So there if you go and check out the problem number 690, so that is this problem. So which is saying that you have a real valued function and for any 2 points in its domain x, y, the absolute difference between f of x and f of y is less than equals to half times x, the absolute difference between x and y. So now, given this, we have to prove that how many fixed points does the function have. So the next line that you see, that how many points of intersection the graph of y equals f of x and the line y equals x, they are intersecting. So that is nothing but we call those special points as the fixed points of the function. So suppose this is the line y, so this is the line y equals x, and suppose for any function, not for this, like your function, the graph is like, for example, this. So then wherever it's intersecting, suppose that point is x naught, so then you have f of x naught to be equals to x naught. And so those special points are known as the fixed points of the function. Now it might happen that your function graph is not even intersecting the line y equals x. Okay, so then no fixed points. Now it might happen that it's intersecting more than once. Okay, so these are the main things. So we have to consider. So now given this condition, they are asking how many fixed points are there. So I have generalized this problem. So the generalized version, what I have done is basically all the conditions are the same. Only I have replaced this half by lambda. And lambda is strictly between 0 and 1. Okay. The rest of the problem is the same. So now that means even if you replace half by any value between 0 and 1, still between 0 and 1, half, 1/4, 1/3, or any irrational value also. So but it has to be between strictly 0 and 1. The answer will remain the same. And so the answer as is given, that we have to prove that it has one fixed point. So we have to show that it has a fixed point, and we have to show that it's unique. Because if you don't show the uniqueness, so what happens is that one can also argue that, okay, you have shown that it has a fixed point. Now it can have more than one fixed point as well. So since there are options like 0, 1, 2, so, and also none of the following numbers, so question arises that whether we have more or not. So now the very first common mistake I want to talk about, I've seen many people do, is they straightforward differentiate to get their answer. Okay, so you might get your answer, I'm not denying. Okay, but the thing is that since it's not given that your function is differentiable, so you cannot differentiate it. Okay, and also if you want to differentiate, you can prove that your function is differentiable using the definition of differentiability and so on, and then after that you can differentiate. Okay, but you see that in the problem also it's not given that your function is differentiable. And moreover, like these type of functions are known as Lipschitz function. Okay, Lipschitz, Lipschitz function. And all Lipschitz functions are not differentiable, but all Lipschitz functions are continuous, and moreover they're uniformly continuous. Okay, so now for high school students, forget about the word uniformly. So for grad students, you must be knowing what is uniformly continuous. Now coming back to the problem, yes, for Lipschitz function you don't have to be like, lambda doesn't have to be strictly between 0 and 1, just lambda has to be strictly greater than 0. Okay, but for our problem, this is a special problem, this is a special property. So for our problem we require lambda to be between 0 and 1. Okay, so first let's come to the continuity part. So I'm claiming that f is continuous. Okay, so what is the proof? So the very first thing is that for the grad students, like if you know the definition of epsilon delta definition, you can use that given epsilon, you can easily figure out a delta such that whenever this x minus y, the difference for absolute difference is less than delta, so f of x minus f of y will be less than epsilon. And for the high school students, what you know is the sequential criteria. That is, you know that limit x tends to y, so f of x, if it is equal to f of y, or you must be getting confused about x and y, so let's use c. So limit x tends to c, if f of x is equals to f of c, then we say that the function is continuous at the point c. Okay, So just at the point C, not everywhere. So now let's use this thing. So this is the sequential criteria. What is the sequential criteria says is that f is continuous if and only if for any sequence. So it's an if and only if condition. So for any sequence which is tending towards C, let's say xn is tending towards C, then f of xn also tends towards f of C. And if this happens, that is for all sequences with xn which is tending towards C, f of xn is tending towards f of C, then your function is continuous. Okay. And if your function is continuous, then this happens always for any sequence. So now, so this is what in short, like in compact form for the high school students, you have this. Okay. So now, so whenever you see this, you say that the function is continuous at C. So now let's see. So the condition that is given, so I can since it's valid for any two points in its domain, so let's replace y with C. So f of x minus f of C is less than equals to lambda times mod of x minus C. Okay. Now you see that if we have that is x is tending towards C, then it implies that mod of x minus C is tending towards 0. And if you even multiply it with lambda, because lambda is not equals to 0, so this also goes towards C, which implies that mod of f of x minus f of C goes towards 0, and which implies that f of x tends towards f of C. Okay. So for the high school students, like you are able to prove that this function is continuous. Now, what is our major claim or the major proof? That we have to prove that there is a fixed point and it's unique. So first, let's come to the fixed point. So our claim is that f has a fixed point. Coming to the uniqueness later on after proving that it has a fixed point. So now what's the proof of this? That is, what we'll do is we will take any arbitrary point in its domain. So again, let's take any arbitrary point C in its domain. Okay, one more thing I forgot, like we prove that f is continuous throughout its domain. Why? Because C was any arbitrary point in its domain. Okay. So now let's again take any arbitrary point from its domain C, and after choosing that point C, we will fix it. So C. Okay. Then we will take f of C, then f of C, and then f of C, and so on. I hope you're getting, like, I'm building a sequence starting with that point C, and then f of C, f of C, and so on. So let's say that this is the 0th term of the sequence, first term of the sequence, second term of the sequence, third term of the sequence, and so on. So we have a sequence. Now let's try to talk about the convergence of the sequence. Now, mostly talking about the convergence of real sequences, we have like major two definitions that I always teach. That is the very first thing, when you know where it's converging, when you know the limit point L and you use the epsilon definition, so then you have to know where it's converging. Okay, then you have to, like, for example, we know the sequence, like for example 1 by n. We know that we can intuitively think that it's converging to 0. Okay, so we know L, and now we can show that using the definition of epsilon, we can show that that is the limit point of that sequence 1 by n. But where we don't know the limit point L, what do we do? So we try to show that the sequence is a Cauchy sequence. So we try to use the Cauchy definition of convergence, which says that given epsilon, there should be a, so given epsilon greater than 0, depending on that epsilon, we will be able to figure out a stage, kth stage, after which if you take any two terms of the sequence, their difference will be less than epsilon. So for any given epsilon greater than 0, if you are always able to figure out a stage after which you pick up any two terms of the sequence, their difference is less than 0. So, sorry, their difference is less than epsilon. So then you are able to prove that it's a Cauchy sequence. Okay. So now, again, coming back to proving that it's a Cauchy sequence. So let's try to figure out the difference between two consecutive terms of the sequence. So xn minus xn minus 1. So now, what is actually xn? So if you look at x3, so what is actually x3? It's nothing but f of x2. What is inside is nothing but x2. Okay, f of x2. So this I can say that this is f of xn minus 1. minus f of x n minus 2. And now if I use this criteria, that is less than equals to lambda times the difference between x and x minus y, so I can write this is less than lambda times x n minus 1 minus x n minus 2. Again, if I repeat the same procedure, so I'll get another lambda, so lambda square less than equals to lambda square x n minus 2 minus x n minus 3. Again, lambda cube x n minus 3 x n minus 4 and so on. Okay, so if I keep on proceeding like this, so where will I reach finally? So it will be boiling down to x1 minus x0, the last the initial two terms. But then the question remains is lambda will be there, but what will be its power? So let's look at the pattern that is developing. So you see minus 1, so power is 1. Minus 2 power is 2. Minus 3 power is 3. So here it's 1. So 1 I can write it as n minus 1. So that means the power will be n minus 1. Okay. So now we have come to the conclusion that is x1 and x0, they like, since C was, after choosing arbitrarily C from its domain, C was fixed. So x0 is fixed even since the function is given. So f of C, which is x1, that is also fixed. So these are two, like this difference is a particular real value. Okay. And then we have multiplied by lambda to the power n minus 1. Fine. So now you see that lambda is also fixed. And so the difference between two consecutive terms, we can see that it's bounded. Okay. So now even if you want, like, you see lambda is strictly between 0 and 1. So lambda to the power n minus 1, whatever it is, it's less than 1. So you can easily write this is less than mod of x1 minus x0. So we have proved that, like, the difference between two consecutive terms of the sequence is bounded. Okay. So now let's try to figure out the difference between any two terms of the sequence. So let's take that, let's say n is greater than m, and let's discuss the difference between xn minus xm. So here now try to understand, I'm taking any two terms, their difference. Okay. So what I can write this as, like, xn minus xn minus 1 plus xn minus 1 minus x n minus 2 plus xn minus 2 minus xn minus 3 and so on and so forth till we have, like, x1 minus x0. Okay. Sorry, I made a mistake. We are going till xm. So x here xm. So m is like the last thing that we will be reaching. So that means it will be xm plus 1 minus xm. Okay. Fine. Now what? Like, we can use the triangle inequality and write this as less than equals to xn minus xn minus 1. Why did I do this? Because I have already bounded the difference between two consecutive terms. So proceeding like this, we have xm plus 1 minus xm. Okay. Now try to figure out that, look at this criteria, that is xn minus xn minus 1. I can write this as less than equals to lambda to the power n minus 1 times x1 minus x0. So this will be, I can write, so what will be this? Like, this will be lambda to the power n minus 1 times x1 minus x0. So that x1 minus x0 mod, I'll take it common. So from the next one, I'll be getting lambda to the power n minus 2 and so on. The last one will be giving me lambda to the power m multiplied by mod of x1 minus x0. Okay. Now you see that I can write this as like lambda to the power m plus lambda to the power m minus 1 and so on. Like I'll take the infinite sequence. So what I'm doing is, you see that n is greater than m. So lambda, so what this is having is terms from lambda to the power m, lambda to the power, sorry, m plus 1, lambda to the power m plus 2 till lambda to the power n minus 1. Now I'm continuing that further. Like I'm adding to that sum lambda to the power n, lambda to the power n plus 1, lambda to the power n plus 2 and so on, all the powers. Okay. So then I have this inequality as well. Okay. And multiplied with x1 minus x0 mod. Now you see that this is an infinite GP series, and also like lambda is strictly between 0 and 1, so we have the sum. Okay, so this is nothing but lambda to the power m by 1 minus lambda, okay, multiplied by x minus x0. Now you see that since lambda is strictly between 0 and 1, 1 minus lambda is again fixed. So the denominator is fixed there. X1 minus x0 is also fixed, so that is also fixed. But this lambda to the power, now I can increase my m as large as possible, and I know that if like I have a number between 0 and 1, and if I take its power higher and higher and higher, so that number goes to 0. So that means it tells me that so I can see this as lambda to the power m, and the rest is constant. Okay, so something constant, like let's say k. So now I can make this lambda to the power m, I can increase my m, and lambda to the power m will tend towards 0, making this thing as small as I want. Okay, so then it basically tells me that if you want to make the difference between any two terms xn and xm less than something, you just have to increase your m, and after a certain stage xn minus xm, their difference will be less than that, because as I said, like I can make this difference as small as I want. I can just I have to just increase my m. Okay, I'll keep on increasing, and after a certain stage, because this whole thing will be going towards 0, so after a certain stage, whatever be my epsilon, so this xn minus xm will be less than epsilon. So proving that this sequence is a Cauchy sequence, and any real valued Cauchy sequence is, so again, those who are not sure what is a Cauchy sequence, you are hearing it for the first time, just go and check it out. So we have proved that xn, so the sequence xn is a Cauchy sequence. Okay, and which implies that the sequence xn converges. Okay, so now our sequence converges. So let's say that let xn converges to L. Okay, we don't know where it converges, so arbitrarily, like let's take that it's converging to L. So what does it mean? It means limit n tends to infinity, xn is equal to L. That it all means. So now what we have is, we have that sequence, and we have proved that the sequence converges. But now you will say that where is the fixed point of the function? Okay, so now you see that, like, what is xn? So that is limit n tends to infinity f of x n minus 1, that is equal to L. Okay, and now we have proved that our function is continuous. So we know that that is also equal to, the limit can go inside, n tends to infinity x n minus 1, and that is also equals to L. And now I know that this thing is also, like, that is xn minus 1 and xn whatever, so that is the same sequence xn, and that converges to L. So that implies that f of L is equals to L. So wherever that sequence goes and converges, so suppose if it is L, so that point is the fixed point of that function. Okay, so we have proved that the sequence converges. So obviously it converges. So it's a real sequence. So it converges to some real value. So that real value where it converges, so that is the fixed point of that function. Now you see that the very interesting part is the next part, where you have to think that where we would be now claiming that. So the next claim is that uh, f has a unique fixed point. Okay, so now if you look at it, just that proving that, okay, I have to just prove that it has a unique fixed point, that is fine. But you can also look at the interesting part, that is, we started with, we picked up any arbitrary point C from its domain, and then we fixed it, and then we produced the sequence, and this sequence is converging to L. Now someone can easily say that if I suppose I started with C equals some value, just for example, let's say 1. C, I started with C equals 1. Okay, 1 is in the domain of F. For example, I'm saying. Now, some other student can come and say that, okay, I'll not start C with 1, I'll start C with 1.5, or let's say C with 1.2. So then, if I prove that, like, this sequence, like, wherever it converges, so that is the fixed point of this function, so that, and it's unique, so that means whatever be the starting point, it doesn't matter. Always this sequence will converge to the same point. This is the interesting part to look at it like this. Okay, so it doesn't even matter which C you are picking or which point you are picking in its domain and making this sequence. Always the sequence goes and converges to only one point, one fixed point. Okay, so let's try to prove. So how do we prove that? So we usually prove this uniqueness by contradiction. That is, no, let we have two fixed points. Okay, so let F has two fixed points. So what are those two fixed points? Let's say x0 and y0, or let's say L1 and L2. Okay, L1 and L2. So what does that mean then? That is, f of L1 is equals to L1, and f of L2 is equal to L2, because I'm saying that L1 and L2 are fixed points, and we are considering that L1 is not equals to L2. Okay, now look at the given condition again. If we start with again f of L1 minus f of L2, so by the condition this will be less than lambda times mod of L1 minus L2. Okay, but again, what do we know? This is nothing but f of L1 is L1 and f of L2 is L2. So now you are getting that mod of L1 minus L2 is less than equals to lambda times again mod of L1 minus L2. Now suppose you have a positive quantity and you're multiplying that positive thing, positive real number, with something lambda which is between 0 and 1, strictly between 0 and 1. So that will make it further smaller. How can it be equal or larger? So this is the contradiction we are having, and thus, since we are getting contradicted, so that means our hypothesis, which was that it has two fixed points, is wrong. So that means it has a unique fixed point. And so like, the name is contraction mapping, because here is like, here the thing is that here and here you are making the contraction. Okay, so you can, like, the difference between any two arbitrary terms, you can make it as small as possible. So after a certain stage, obviously, so not always. So that's where the thing, the name contraction is coming from. And yeah, so now we have proved, and so basically the answer will be B. So now if you know this result, even if half is replaced with anything strictly between 0 and 1, so the answer is going to be one fixed point. And yes, so if you have enjoyed the solution or the video or the problem or anything, so just put a like and share it among the other students who are interested in learning these type of mathematics and the detailed explanations. And yeah, so yeah, thanks for watching, and keep watching and keep learning. And I'll be coming up with more such videos soon. And also we are going to launch our workshop or the crash course for ISA-CMI BMAT BSTAT this year. And also we are going to launch our new courses for the next batch or the next years. So yes, like tomorrow I make the announcement. And yeah, that's it for this video. So thanks for watching. See you in the next one.